Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. From today's lecture, we're gonna talk about nano-imprinting, which is Unit 3. Today we're gonna talk about thermal nano-imprinting, Part 1. In this part 1, we're gonna mostly talking about the lithography system used for thermal nano-imprinting. So let's just briefly compare the two technologies used for the nano-imprinting. As to the nano-imprinting, that is based on the resist type, which is coded for a substrate on a substrate. Based on that material, we have two techniques, thermal and then UV nano-imprinting lithography. As the name implies, the thermal nano-imprinting use the resist, which we will transfer our patterns to the material. And then that material, the resist material, is a thermoplastic. So it can be cured by heat, so that is why we apply heat. And then for the resist used for the UV nano imprinting, it is kind of photosensitive material, which is very similar to the negative resist used for the optical lithography. So upon we apply UV light on that material, those kind of liquid form of the materials becomes solid. So in a sense, it is kind of pretty similar to that negative resist used for the optical lithography or e-beam lithography. As to the resolution, both of the technologies offer a pretty good resolution. And then it is pretty fast. So the throughput of those kind of technologies is kind of pretty fast. And one of the big differences between thermal nano-imprinting and the UV nano-imprinting is as to the thermal nano-imprinting, it has difficulties in alignment. So if we wanted to use thermal nano-imprinting for the multiple layer of the pattern definition, then it's kind of very hard to use it for an alignment from the previous existing patterns to the another kind of patterns on the mask, on the master mold in this time. But UV nano imprinting does not have that kind of a problem, and it also provide very precise alignment. So we will go through all these kind of details as we talk about all these kind of detailed technology. So let's talk about a little bit about the thermal nano imprinting. This is the overview. So as you can see from the FESEM images on the left, so this diameter of the hole is on about 10 nanometers. So as I just mentioned briefly in the previous slide, this thermal nano imprinting lithography can offer this kind of very high resolution pattern transfer. So far it is about 4 nanometer feature size was demonstrated using this kind of thermal nano imprinting lithography. So the thermal nano imprinting lithography itself is kind of very simple and then offers very high resolution, which is compatible with e-beam lithography. And then the process is kind of very simple. So when you have a substrate coated with the resist, once we just press the resist using a master mold, that is and then separation is the one single step for the thermal nano imprinting. So in a sense, this kind of process will be is kind of very easy. Another big advantage out of this kind of nano imprinting technology, not only for this thermal nano imprinting, but also for the UV nano imprinting, if we can make these kind of three-dimensional structures, if then with one single lithography process, we can transfer this kind of a very complex three-dimensional pattern transfer is also possible. So this slide, the picture shows the example of the three-dimensional mold. So this is the structure on the mold, master mold, and then when we press this master mold on the resist material in this time, this is the thermal plastic. If then those structures is kind of transferred as it is. But as you may expect, every time we want to do pattern transfer, this master mold always should directly contact the resist material. So you may remember when we discussed about the contact lithography technology at the optical lithography, one of the biggest drawback of that technology is on those kind of contact optical lithography, the mask always should contact the photoresist. So that is why we worried about those kind of contamination or damage on that photo mask. But the case of the thermal nano imprinting is much worse than that of the contact optical lithography, because for the contact optical lithography, those kind of mask just touch the resist coated substrate. But for the thermal nano imprinting, this master mold not only contact the resist, but also we apply pressure between this master mold and then resist coated substrate. So this master mold has much higher chances for the damaged or contaminated. So that's the one of the problems this thermal nano imprinting lithography has. And then, as I just briefly mentioned in the previous slide, the master mold for the thermal nano imprinting are mostly made out of the silicon wafer, which is not transparent. So that is why we will discuss about this issue in the later of the slide. But since the master mold is not transparent, so that is why it's kind of very hard to align the markers on the master mold to the alignment markers formed on the substrate. So that is why in most of the cases, the alignment margin is kind of bigger than 1 micrometer. So it is not acceptable for those kind of nanoscale pattern definition. So this is another kind of a big problems out of this kind of thermal nano imprinting lithography. And then when we make the master mold, when just considering this master mold is as a cylinder shape, if then from the side view of this cylinder, the best side angle we can get is 90 degree. And in most of the cases, it is kind of a little bit angled, something like this, like a pyramid. So if we just imprint using this kind of structure, if then the resulting images are transferred to the resist is something like this. So in this case of that, when we wanted to use this kind of patterns, this is a resist and this is a substrate. If we wanted to use this kind of angled resist patterns for the lift-up process, as you can expect it when we deposit film on this pattern transferred substrate, all these kind of films are continuous. So when we do remove this area during the following lift-up process, these films are all continuous. So that is why it just most likely end up with forming this kind of a radial structures. So this thermal nano imprinting process is not good for a lift-up process as well. So just going back to that performance measures for evaluating the lithography technology, this thermal nano-imprinting lithography technology provide very high resolution feature, which is smaller than 5 nanometer, and then it also provide throughput, which electron beam lithography or ion beam lithography cannot offer. But it is pretty good for the high throughput production. But this is the alignment accuracy is the problem for this technology. So what do we need for thermal nano imprinting process? So it is something like very similar to making waffles or playing with the Play-Doh. So we need somehow this kind of a master mold, which has a physical design we want to transfer. And then we want some kind of a material. This is the thermal plastic in this time. And then we need a pressure, or we need heat. So we need those kind of three factors: master mold, thermoplastic, and then energy like heat and pressure. So if we do have this 1, 2, 3, we can successfully do this kind of a thermal nano imprinting lithography. So before we talk more about the processes, let's talk about those kind of resist. So we are using thermoplastic. So this thermoplastic is kind of a state, just changes as we just increase the temperature. So for these techniques, the glass transition temperature, in another word, we call that as a TG. This glass transition temperature is kind of very important. And this is a very important parameters for this thermoplastic. So what happens is when we increase the temperature higher than glass transition temperature, those kind of a spin casted resist, thermoplastic resist becomes in the state between liquid and then solid. So as those kind of material is heated higher than glass transition temperature, it is not perfect solid, and then as we just it is more soft state. So as we just apply little heat, this material is kind of ready to flow, but those kind of flow is kind of very viscous. So that is why it is not in the flow state like a liquid, but it is a kind of a state very kind of a soft, so it can just flow as we just apply a pressure. So we will talk about those kind of recipes, typical recipe used for the thermal nano imprinting lithography. But this glass transition temperature, based on this temperature, we can just make a recipe for the thermal nano imprinting lithography. So what's the typical process step of the thermal nano imprinting? So first, as we do the optical lithography, we just spin coat these thermoplastic materials on a substrate using spin casting. So it's kind of the same, just a spin coating process. And then this is the master mold. And then we place this resist coated substrate and then master mold. And then at some point, this master mold just lowering and then contact the resist and press. And then at some point, this master mold and then the resist just separated, and then we always have this much of the residue of the resist. So using the following oxygen plasma cleaning, we remove those kind of very thin layers, and then we can finally achieve this kind of structures. Those kind of oxygen plasma cleaning step, in other words, some people call that process as a discoming process. So that discoming process means just removing those kind of very thin polymer layers between the patterns we want to finally achieve. So this is the typical recipe we want to use. So at this point in room temperature, when we have on the previous slide, this is a resist coated substrate, and then we have that master mold separated. So this is the state when we just have in this state, it is kind of separated. So we will have a, depends on the system, it has a two heater, and then it could have a one heater. So in this case of that, this system needs a two heater on the master mold side and then substrate side. So we will heat up those kind of substrate side heater and then master mold side heater. So that is why there is some kind of temperature discrepancy between heater number 1 and heater number 2. So we wait until these two temperatures pass the glass transition temperature, which the thermoplastics are getting much more soft. So once those kind of two temperature reaches to the embossing temperature, and then once those kind of two temperature just reaches to that tightening temperature, we lowering this master mold and then apply the pressure. So for example 10 bar, and then we will hold some time at this specific temperature with this kind of pressure for some time. It could be on 5 to 60 minutes, depends on this embossing temperature. And at some point we just turn up the heater. So the heater number 1 and number 2 turned up, so the entire temperature of this master mold and then resist coated substrate is cooling down together, but still we maintaining the pressure. And then when it just going down lower than glass transition temperature, we still holding the pressure. And then at some point we just remove the pressure, and then as those kind of temperature for master mold and then substrate getting closer to the room temperature, we just separate the master mold from the substrate. So this is not kind of decided, but as a rule of thumb, as to the embossing temperature, people normally use about 50 to 100 Celsius degree higher than glass transition temperature. And then as to the this point, we are removing those kind of pressure. People should wait until this temperature is kind of more than 10 Celsius degree lower than its glass transition temperature. And then as to the final separation of the mold and then resist, people normally wait until it reaches to the closer to the 50 Celsius degree. So what happens is if we just separate at this point higher than glass transition temperature, what happens is in this case of that, if we just separate master mold from the resist coated substrate, let's say this is the resist, at the temperature higher than glass transition temperature, what happens is this resist is still very soft state. So that is why these patterns we just transferred by the pressing process can reflow. So instead of having just maintaining these sharp edges, it can just reflow. So it can just make this kind of round structures. So that is why we want to wait until the temperature cooled down, cool enough, which is lower than glass transition temperature. All those kind of resist is kind of much closer to the solid phase. So we wait until that resist turning back to its solid form, and then once we reaches that kind of a low temperature, if then we just remove that kind of master mold from the resist coated substrate. So there are two types of the system, and one is the piston type, and another one is an air cushion type. So the piston type is kind of very simple. It has this kind of sample stages, and then we load our samples on these sample stages, and the master mold is mounted on the piston. So when we want to apply the pressure, physically these pistons going down and then just to press. So that is the kind of piston type of the thermal nano imprinting lithography system. But in this case of that, if we are using kind of a very small piece samples, if then depends on how those kind of thickness are uniform, or what's the roughness of those kind of master mold. Those kind of pistons cannot apply even pressure. So in this first case, if the piston is kind of a little bit tilted, if then when the piston coming down and then apply the pressure, this left side of the samples experience much higher pressure because this piston is kind of a little bit tilted. If those kind of piston has this kind of very rough surface, or this master mold has a very rough surface, in the case of that, it also cannot apply even pressure from mold to this substrate. And then if we have a master mold which has this kind of a curved backside, it also apply the pressure, the center area, the pressure is kind of much higher. So this kind of piston type may have a problem for this kind of uneven pressure application. So people developed another kind of a way, which is an air cushion pressure. So what this one is, people just put this resist coated substrate and then master mold in a plastic bag, and then apply this entire structures by air. So instead of just the piston type, it only apply heat between the master mold and then substrate. But for this air cushion type, it just apply the pressure to the chamber. So it is kind of very similar. People just dive into a deep sea. If then, no matter what kind of irregular shape would be, everywhere will experience the even pressure. So this is the based on that kind of an idea. So as we just apply, no matter what that surface of the master mold is kind of rough or round, when we apply the heat pressure, to the chamber, if then everywhere will have the even pressure. So that's it does not have those kind of uneven pressure application. So in a sense, this way is kind of much more preferable. So this is an actual tool using that piston. So as you can see, it has computers, and then this is the chamber, and then this is the holder, and then this chamber is just opened over here, and then this is the piston. So this piston type for the thermal nano imprinting lithography, one of the possibility forming pressure, forming defect is an air bubble trapping. So just considering we are using 8-inch wafer, which is a pretty big size. Actually, for the commercial production, we are using 12-inch wafers or bigger now. So just considering our kind of master mold is an 8-inch wafer, and then the substrate is also 8-inch wafer. And then at some point, when this upper stack and then the lower stack reaches the embossing temperature, which is higher than glass transition temperature, and then upon we need to apply the pressure, since this kind of radius of the substrate and the master mold is kind of pretty big, if we just suddenly apply the pressure, some of the airs cannot escape properly, and then once those kind of airs are trapped in somewhere, it just prevent this master mold touching the substrate, and then that area, air bubble trapped area, remained as a defect. So to reduce that kind of problems, people just used this kind of flag, which is about 50 micrometer thick. This kind of triangular shape of the very thin metal film. So what happens is from the top, if this is a 4-inch wafer, 8-inch wafer, those kind of flags just inserted first, and it just physically separate the master mold and then substrate, and then we just increase the heat over the embossing temperature. So just right before we apply the pressure to everywhere, there is another kind of rod positioned in the middle. So those kind of stick just coming down and then press the middle first, and then this chamber is kind of keep evacuating, so under the vacuum. So this spacing between the master mold and then resist coated substrate keep evacuating, and at some point, so since this bar is kind of pushing in the middle, so it is kind of a little bit kind of bended like this, and at some point this flex coming out, and then at the time the piston just press the master mold. So this way we can minimize the air trapping. So that's the kind of a way people are using to minimize those kind of possibility of the air trapping. And then this fixture is for the flag. And then this is the little bit bigger pictures I showed you from the couple slide before. So since this is the substrate holder, so these three things are flag, and then these entire substrate holders can be hot when we take out from the chamber, depends on when we take out the samples. So that is why we sometimes need to use these tweezers to handle this substrate holder. this is the cooling chuck. So sometimes we can further cooling down the substrate on this cooling chuck. So this is the water cooling chuck. So this surface of the black disc is kind of pretty cold. So using that way, we can just cooling down the substrate much faster. Another interesting point is when you have a very thick master mold thickness and then substrate, actually the system does not know what kind of thickness of the master mold and what kind of substrate thickness we're gonna use. So here is the ruler calibrating those kind of thickness of the master mold and then substrate. So if this is 1 millimeter and this is 1 millimeter, if then we just adjust the height, total height 2 millimeter over here. So when piston just coming down and it is kind of separate, this is the substrate holder. So when a piston reaches to the 2 millimeter above substrate holder, the machine thinking about it is the 0 point. So it just started to stop at this point and then just apply the pressure. So without this kind of a calibration, since the machine does not know this kind of a thickness variation, so in this case of that, it is kind of a more likely master mold and then substrate just to crush it by the pressure application. And this is another kind of a side of the view, and this is the ruler, and then this is the tweezer, and then this is the computer. And then the chambers kind of open this way. So using that tweezers, we can just load the stacks to the chamber. So this is the one of the example of the piston type thermal nano imprinting lithography tool. And this is another kind of an example using air cushion type. So this is also used for the thermal nano imprinting lithography. So instead of those kind of chambers kind of opened this way, it just uses this kind of a drawer. So this is the chamber, and then we're gonna apply pressure to this chamber evenly. So to load the sample, we just take this drawer out, and then we put this kind of a substrate holder. So this is the thermocouple. So on this thermocouple, the way of we are loading the sample is we put the plastic bag around this substrate holder, and then load the resist coated substrate and then master mold, and then we put another kind of a thin plastic bag on top. So that is why we can just load all this stack, master mold, substrate, and then which is left by the this kind of plastic bag. And then we use this kind of fixed metal fixtures to hold that plastic bag and then the stack of the master mold and then substrate. So first, and then we just transfer. This is the picture. We just transfer entire substrate holder to the drawer like this. So and then we just close that drawer, and then it is kind of ready to apply the increase the temperature and then pressure. So one important thing is for this one, when we have this kind of wrap, we first evacuate the plastic bag. So using this kind of vacuums, we just seal this master mold and then this resist coated substrate more tightly. It is something like we can buy those kind of a vacuum seal from Walmart or those kind of retail stores, which is used for some kind of a food storages or things like that. So as to the evacuation, it is kind of a very similar mechanism to make these stacks get together much tighter. And once we just evacuate these plastic bags, then we increase the temperature. And then since in the middle of this stack, as I showed you, there is a thermocouples already mounted. So those kind of thermocouple just giving a feedback. So based on that, we just increase the temperature to the embossing temperature, which is higher than glass transition temperature. And at some point, we apply the pressure and then wait for some period of the time, and then release the pressure, and then just waiting for the cooling down. So as to the rest of the processes, it is kind of very similar to what we are doing using the piston type of the thermal nano-imprinting lithography. So today we talked about the system used for the thermal nano-imprinting lithography. So as we discussed, it only needs one single press. So that is why it is kind of very fast, because the entire wafer can be processed by one simple press process. So that is why it is kind of fast and it is simple. And then the thermal nano-imprinting lithography offers very high resolution images, and it also offers three-dimensional pattern transfer with a single process. But and those kind of systems for doing this thermal nano imprinting, there is a piston type and air cushion type. So next lecture, we're gonna talk about the resist used for the thermal nano imprinting, and then we also will talk about the issue for the alignment. See you next time.